And if you remember, we finished off yesterday by saying, well, we could take all of these geometric properties that the manifold associated with the functional objects of interest are endowed with, namely the metric tensor and the connection, and we could then start to define mechanisms that will allow us to develop a proposal mechanism and therefore a transition kernel for a Markov chain Monte Carlo method that would exploit these geometric properties. Okay, so in other words, we would be defining a Markov process in the natural space that these functionals reside in. And so what we did is we took the stochastic differential equation that we had employed, which defined a diffusion. It was a diffusion that was developed with Euclidean, within a Euclidean coordinate system. And what I said right at the very end of the last lecture was, we'll now take that very same diffusion process, the Langevin diffusion, and we'll now define it on a Riemann manifold. And just to cut the long story short, we'll then take the Euler-Maruyama second order integration step. And so this is the discrete form of that diffusion. And we had a look at a few things, a few characteristics of it. We noticed that the gradient now had the proper contravariant form. We also noticed that the components of the connection were appearing here, so clearly if there was any strong curvature across the manifold, then that would be taken into account as we diffuse across the manifold. And probably the most obvious thing that was really going to be useful is that rather than having this spherical diffusion, this spherical innovation process, we've now got this square root linear operator acting on these spherical Gaussian variates. And in essence, what this is doing is inducing correlation structure which is local to the point at theta. And so every point on the manifold is going to have this local covariance structure. And so hopefully I convinced you that, well, this looks quite promising. Now, let's just assume that the manifold has zero curvature, or constant curvature, I should say. Then this term will disappear, and we're just left with something that looks pretty familiar. If you remember when I presented the Langevin proposal mechanism, the main issue was the sphericity of this diffusion, and I said that what numerical analysts would typically do is they would precondition the system of equations with some sort of matrix, and of course the question was, well, how do we select this matrix? Is it a global matrix? Is it a constant matrix over the whole space? Or is it going to be one that will change depending on the phase of the Markov chain, whether it's still in the transient phase or whether it's actually converged to the invariant distribution? Should it actually be defined at each point on the overall process? And of course the question was, well, we've no idea. But if you look at this simplified form of the diffusion, you can now see that the preconditioning pops out as just these functionals of the metric tensor. And indeed, if the metric tensor is defined at each point in the manifold, then we have this point-specific preconditioning. So this looks good, looks promising. And if we then use this to define a proposal distribution, remember these are standardized normal variates, so this is going to have a distribution which is normal with a mean, which is just going to be this component here, and the covariance structure is just going to be the square, so the matrix square of this term here. And so here we write our proposal mechanism as a normal distribution with a mean which is a function of the current position and the chosen integration step size. And now we have a covariance structure which again is a function of current position and scaled by the square of the integration step size. Now, of course, because we've discretized this, this is just a proposal. We therefore define the overall transition kernel by the product of our proposal and our acceptance probability, which in this case is just the standardized, the standard Hastings type acceptance probability. So in other words, the proposal mechanism now diffuses approximately along the manifold. So if you remember my little pretty poor cartoon of the manifold, it's too early in the morning to put any effort into that. But if we had some manifold that looked something like this, and it was in some sort of ambient 3D space, and then what this proposal mechanism is going to do is make sure that the diffusion stays, certainly approximately, on the manifold. So probably a nice example would be Neil's rotated sixes and so forth. Right? So this is the one manifold that these sixes reside on. Now, if we were to devise a Markov chain on these to explore this, and we didn't take into account the fact that we were operating on this this manifold structure, then our proposals in the original 600 dimensional space would be all over the place, and it wouldn't in any way respect this this submanifold which in essence all of these objects resided on. But again, because our diffusion process is now defined in the manifold, we're going to have a diffusion which is going to move along the manifold like this. And that's exactly what we want. So that looks great. Now, someone came to me just before the lecture and complimented me on how lucid my presentations were and how exciting this work was and so forth. But said it would be good to hear about applications. Well, I would say that I'm probably more an applied statistician than theoretical, certainly not theoretical at all or methodological. And there is a ton of applications, of very serious applications, that I had planned to talk about. But given that what was meant to be a 2-hour lecture is now looking like a 6-hour lecture, what you'll have to do is look at some of the examples in the other slides, which I believe are on the website. And you'll see some very compelling applications from real science. Okay, so we're working with physical scientists, petroleum engineers, with life scientists, and the only way that we can really crack some of their modelling problems is to adopt or to exploit the underlying geometry in the statistical models. But in the grand tradition of machine learning, I will ignore the real applications and focus on a little synthetic toy one. But this is a really illustrative one. So what I've done here is I've plotted the posterior distribution of the mean and the variance of a standardized normal after I've observed 30 data points. So the mean, the actual mean was 0, and the standard deviation was 10. And there were uniform priors. Okay, so I didn't put the sort of appropriate conjugate priors on it. Now, if I use the proposal mechanism based on the standard Langevin diffusion, where I have just defined it in a Euclidean coordinate system, then here is my Markov chain. Starting from this point here, starting from the point sigma mu, 45, we see this nice random walk, right? So we also see that the expected value, the average value of the step size is round about constant. So that looks good. And you can see, well, you can't really, but you can see certainly that it's following a direction. There's certainly a random element, a random walk element to the chain, obviously, but the directional derivative is certainly helping things to move along. So we can see that in the transient phase of the chain, everything is nice and well behaved, and then we converge and everything is fine. On the other hand, if I take into account the geometry of the hyperbolic space of the univariate normal distribution, and I define my Markov chain using the associated metric, then we get something that looks like this. So you can see that we're taking far larger, or making far larger proposals and accepting them. So the convergence, so that the length of time that the chain spends in the invariant, in sorry? Yeah, thanks. In the sort of burn-in phase is much shorter, and we converge much quicker to the stationary phase and sample efficiently. Now, if you remember the picture that Escher had of the hyperbolic space, right? So the little demons and angels defined, in effect, a uniform grid, and this is exactly what we've got here. Is that this is a kind of uniform step in the appropriate space that we're dealing with. Right? So the metric structure is kicking in here. So so you can see that it takes account of the fact that distances here are not the same in the hyperbolic space, are not the same ways to be interpreted as they are in the Euclidean space. So this looks quite promising. And again, if I show another example where we start somewhere else, again, if we just use the Euclidean coordinate system and the identity metric, then you can see, again, things look okay. Reasonable convergence, but if we take into account the natural geometry, you can see how it's far more well behaved. So far more well behaved in terms of rate of convergence, and then efficient, I'll show you its efficiency of sampling. Well, this is great. And there's already been some theoretical work carried out by one of the leading groups in Markov chain Monte Carlo theory, and actually characterizing the geometric convergence of this manifold-based Langevin-style MCMC method, and the theoretical properties are certainly very exciting. So we'll probably see a theoretical paper analysing these sorts of structures out probably in the next 6 months or so. So this is good. Any questions on that? Yes?
How do the
They're both the same.
They're both the same?
Yeah. They're both the same because the metric, if you remember, is diagonal. And because this is two-dimensional, the inverse can be...
Okay, well, for a two-dimensional problem.
Yeah.
For an n-dimensional problem.
I'll come on to that. Well, you answer the question.
Well, I guess there is some matrix inversion somewhere, so it's probably...
What do you mean you guess? I mean, didn't that kind of give you a clue? Yeah. I'll come on to that, and that's a very good point from a computational perspective. But for a lot, well, for some statistical models, there is structure in the metric that allows you to use various computational techniques to get around that n cubed scaling. And then for an awful lot of others, there isn't. Okay, any further questions before I move on? I'll just pause while I finish this Turkish coffee. Okay, well that's great. But could we do any better? Well, we looked at these geometric properties, and at the end of the day, what we still have, I mean, we're now still relying on some sort of diffusion, albeit on the correct manifold now. But it would be good if we could exploit the fact that there are going to be, you know, what we're doing is we're defining a Markov chain which moves from one point to another. And it would be interesting if we could say, well, there's a multitude of ways of moving on the manifold from one point to another. Right? So there's a number of paths that could be followed. But if we could follow the geodesic, maybe that might actually be a useful thing for devising the Markov chain. It might be efficient in some sense. So why don't we have a look at that and see if it makes any sense. So what I'm now going to do is I'm going to try and exploit the geodesic flows that are natural in the manifold and try and see if we can devise a proposal mechanism that will follow these geodesic flows. Does that sound reasonable? You think your supervisor, if you went up to him and said, I'm going to devise an MCMC method that's going to follow geodesics, you think he would say, yeah, that's a good idea, or, well, I'm not sure.
For me, it's not a good idea.
It's not a good idea. Why not?
Because you ignore the other paths, so you will not marginalize on all the possible ways to go. So it's choosing just the geodesic, you ignore other, you may miss some information.
Uh-huh. And what information would that be?
It's like you rely just on one
path.
transition, and maybe it's a wrong transition.
Uh-huh. How would it be the wrong transition? You know, if you're moving from point A to point B, and you've got a multiplicity of paths that you could follow to point A to point B, why would it not be, what would be the problem of using the shortest path?
But we want to sample from the distribution.
Well, we certainly want to sample from the distribution, but remember, to be able to sample from the distribution, we need to set up these proposal mechanisms to move. So this is just one part of the whole thing. I mean, clearly we want to sample from the distribution, but we want to make the components of the Markov chain that drive the Markov chain as efficient as possible. So this is the heuristic argument, right? This is the hand-waving argument that you're going to make to your supervisor or to your colleagues, and then actually see if it makes any sense. So let's now see if this makes any sense, or if there is indeed a problem with it. Okay? So I would argue, right, I would take the stance that it's intuitive that a proposal that follows the most direct paths, i.e. the geodesics, would seem to be a sensible thing to do. How many of you have heard of the thermodynamic integral? Well, that's a good start. How many of you heard of annealed importance sampling? Okay. So this is difficult stuff then. How many of you have heard of path or bridge sampling? Just one old guy. Okay. Well, as it happens, I had planned to give a lecture on thermodynamic integration and annealed importance sampling and so forth, but you'll have to do the homework yourself by looking at my slides. But let's just, I'm not going to have time to describe what it is in detail, but suffice to say that there is an expression which statisticians have borrowed from physicists to allow them to estimate the marginal likelihood in a Bayesian model. And it turns out that estimating the marginal likelihood using MCMC or sequential Monte Carlo or any sampling method is actually a far more difficult problem than you would first think. And an awful lot of both theoretical work and methodological work has gone into devising sampling schemes which provide unbiased estimates, consistent estimates with low variance of the marginal likelihood or the evidence and so forth. And there is an expression which comes from this whole thing of path integration or the thermodynamic integral as it's called. And just very briefly, the marginal likelihood, if you remember, is the expected value of the likelihood with respect to the prior measure, so in a Bayesian model. So, well, we're all experts in Monte Carlo estimation now, yeah? So if we have our Bayesian model, we have data, P of x, we have some parameters associated with our model, theta, and then we have some prior distribution over our parameters, and then if we integrate over the domain of theta, then of course what this gives us is just the unconditional probability of the data, or the marginal likelihood of the data. And that's the troublesome normalizing constant that appears in Bayesian inference. Now, well, how would we estimate this? Well, we know how to do it. How would we do it? We would devise a Monte Carlo estimate where we would sample from this distribution here, which is the prior, and we would then just use a plug-in estimate. So we would draw a sample from the prior, theta n. We would work out the likelihood. We would draw another sample from the prior, work out the likelihood, and so on. And there's our estimate. And we know that that will converge as n tends to infinity, and it's a consistent estimate and so forth. Let's look at a one-dimensional example. Let's say that for our parameters theta, we put a prior here at some value. And let's say that we then compute the likelihood and the likelihood is kind of well behaved. It looks something like that. What do you think the effect is going to be on this estimate here? Well, let's think about this. We're drawing samples from our prior. Yeah? So that means that all of our samples that are going to go into our Monte Carlo estimate are pretty much going to be here. So And we'll have to wait longer than it's going to take you guys to finish your PhDs, right, before we get samples out here, right? And you're probably going to have a chair at one of the great institutions in the world somewhere once the prior starts putting out samples out here. So what does that kind of tell you about this estimate when n is going to be finite? Would that worry you, or would you just carry on regardless? Because the NIPS deadline was approaching and you had to get an estimate. Or would you sit back and think, this could be problematic? Why? You shouldn't have nodded. Trying to impress. So why would that be problematic? It's going to have extremely large variance, and it's going to take a huge amount of time, because remember that you're taking an expectation with respect to this measure, right, of this function, which is here. So you're only covering this part of the function, and all of this is being missed out. So this estimator, after a dimension of about d equal, or n, d as in the number of dimensions of theta, 1, right, is doomed. Absolutely doomed. Right. So if someone was to say, I want the marginal likelihood for this Bayesian model, and I want the marginal likelihood for this other Bayesian model, and I want to do a comparison of the models based on the evidence, go and work out the marginal likelihood. And you use this here, and you do a few runs, right? Your estimates would be absolutely useless. The variance would be enormous. It would be completely biased. I mean, the bias for finite n would be dreadful, and you know, you could be led to completely false conclusions. So this is serious. And so the other approach that you could take is you could say, well, I could use importance sampling. So rather than sampling from pi of theta, what I could do is I could sample from another distribution, which would be, more, where the mass would actually be more aligned with my target function, my likelihood. And then what I can do is I can just add a weight, right, an importance weight, and correct for sampling from the wrong distribution, and correct with, correct to ensure that the expectation is with respect to this here. Now, why is that a good, or why does that sound like a good idea? Well, it sounds like a good idea because it means that all of my samples are now going to be coming from the regions where this function seems to have the most value. Well, again, to cut a very long story short, this turns out to be a very bad estimator as well. It turns out to be a very bad estimator because it can actually have infinite variance. And empirically, for finite samples, it turns out that there can be an enormous bias in the estimate. And so this is a problem as well. And so what statisticians came up with is they said, well, this is the distribution that we need to be taking the expectation with respect to, but for computational efficiency, we would like to be sampling from something where my samples from my Monte Carlo estimator would be in the regions of sort of high likelihood, i.e. sampling from the posterior. But I know that this is pretty much a flawed estimator, despite it having a CLT and so forth. And so what this turned out to be probably one of the most compelling ways of estimating the marginal likelihood is to define a bridge of intermediate distributions from the prior to the posterior. And you sample from all of these little intermediate distributions, and then you combine them in some way. But as I said, I think that would be a whole lecture on its own, and I can't go into it. But suffice to say that it turns out to be another Monte Carlo estimator, and the variance of that estimate turns out to be a function of the path in the distribution space, so the path from the prior to the posterior that's taken. So in other words, my path could be such that I have a lot of distributions which are very close together at the prior, and then I have a series of distributions which are much further spaced apart as I approach the posterior. Or I might just have a kind of uniform path or whatever. Well, it turns out that there is a functional relationship between the Monte Carlo error and the path that is followed. Okay, so that's what we're going to do. We're going to now look at the Monte Carlo error that's induced by following a path from the prior to the posterior and obtaining an estimate of the marginal likelihood. And so what I do here is I just define a couple of things. Here's my density over data y with parameters theta, and here is an unnormalized version, and this is a normalizing constant. And I'll denote u with arguments y and theta as the derivative of the log of the unnormalized density with respect to the parameters. And theta t is a function that's moving, so that this is a path, theta t, in theta space, and it's indexed by t. Okay? Now it turns out that the thermodynamic integral turns out to be this thing here. Now it's really very simple, so don't panic. But what it says is that if I have a point here, and a point here, these points being distributions, then the logarithm of the normalizing constant of the distribution at the second point over the normalizing distribution at the first point is equal to this thing here. Now what on earth is this thing here? Well, again, it's fairly simple. Let's just look at it. If we've got a d-dimensional parameter space, random variable space of interest, then this here, of course, is the dth element of the vector of the derivatives of the log of the unnormalized density, likelihood. And this here, theta dot d, is the derivative of the path through theta, right, with respect to this index t. And I'm summing over all of the dimensions. And then this function, right, is we take the expectation of this function with respect to p of y, is here, at theta t. Right, so remember that t is defining the path, right, and theta of t is the point in theta space on that path. So this is just the expectation with respect to a distribution at a particular point, theta. And what I do is I then just integrate that expectation over all values of t from t1 to t2. In other words, I take all the points in the path from t1 to t2, and I compute the expectation of the log, the derivative of the log of the unnormalized density multiplied by the time derivative of whatever the path functional happens to be. Now that's the basis for methods which you'll find are in wide use in machine learning, like annealed importance sampling. It's the whole basis of thermodynamic integration. It's the whole basis of population-based Markov chain Monte Carlo. It is also, in fact, a very useful equality for the analysis of sequential Monte Carlo methods as well. But anyway, this was just a sideline. Now it turns out that if we want to obtain an estimate of this here, right, so this is the exact equality, we now want to estimate this, and we have an n sample path, right, so I've now discretized this and I've got n points between T1 and T2, so I've got n distributions between T1 and T2, and I assume independent sampling. Then it turns out that the Monte Carlo error for this here, right, I'm not going to ask you to derive it, but it's fairly straightforward, is just equal to this term here. Well, this is the actual, the square of the actual log ratio of the normalizing constants, and then this is the square, well, this is the expectation of the estimate. And so what you've got here is you've got, so I'm indexing ij, right, over all of the dimensions. So I've got the theta dot for I, theta dot for j at t, and then I've got this thing g sub ij. And g sub ij is just equal to the expectation of these two terms here, product of these two terms, with respect to this distribution. Anyone hazard a guess what this is? Yes? Well, it's the unnormalized, it's the Fisher information of the unnormalized distribution, because remember, yeah? But absolutely, that's what it is. So what we see then is that the variance, so the quality of the estimate of our path integral, or our marginal likelihood, is in essence a function of this metric tensor and the paths that we follow in the parameter space. Now, because you're all experts in tensor analysis, you'll know that if we raise the indices of the metric tensor, right, we can then define it on the cotangent space. And so in other words, what we're now doing is we're saying that this is the ijth element of the inverse of this matrix here. And these pi's are just going to be basically theta dot times g. Does that sound familiar to anybody? Ring any bells from yesterday? This is kind of hard, I guess. But if I write it, if I, like Neil, embrace the sort of matrix and vector notation and go away from the individual index notation, I can write this term in vector notation like this. So there's my metric tensor, which of course is sort of unnormalized, if you will, Fisher information. And here are these velocities in theta space, and I can write it like this, right, for these p's that I defined previously. Now, does anyone recognize what this looks like from yesterday's presentation? Now, I'm really going to have to insist for an answer from somebody. I'll even accept an answer from an old man, of which I think there is only one in the two of us. Yes?
I was scratching my piece out. I was going to say.
Well, that's unfortunate. Right, you're now in the spotlight. What did you think?
Kinetic energy.
Well, exactly. Well, why do you think it's kinetic energy?
Because it's square. I mean, that's it.
It's exactly.
You've got something that looks like mass in the middle, so.
Yeah, we'll go for kinetic energy. Anyone think he's just daft? Old man?
I wasn't paying attention.
You need to concentrate more.
I know this stuff.
Right, electrical engineer. Kinetic energy? Absolutely. Top of the class.
How does an electrical engineer know about kinetic energy?
He knows about Div, Grad, Curl and Maxwell's equations and so forth.
That involves mass and stuff. They only know about charge.
Yeah, well, charge, mass, there's a duality there. Okay. So it's absolutely right. This is nothing more than the kinetic energy which appeared in the Hamiltonian, if you remember, when we defined the hybrid Monte Carlo or the Hamiltonian MCMC method. And so we can write this just as a Hamiltonian in terms of just simply kinetic energy, so there's no potential field. Now this is pretty cool. And I know it's probably taken us quite a bit of time to get here, and I apologise because I probably should have given you a lecture on this previously, but I hope you see the connections that are starting to be made here. That's encouraging. So let's just remember, what we're saying is that the variance of the estimate of our evidence, or our marginal likelihood, right, which is going to be obtained by devising a path, right, from one distribution to another, right, that variance, that error is going to be minimized if we minimize this Hamiltonian. We optimize this here. Okay, so this is H is the Hamiltonian, defined on the manifold whose position-specific metric tensor is G sub ij, computed at each theta. And it turns out, and I won't leave this as an exercise because it's quite difficult, but to define the function, so the path theta t, which optimizes this here, we need to solve this system of we minimize this here. We minimize the variance. We minimize the error induced moving from one distribution to another on the manifold defined by this metric tensor. So we could go directly and solve this system of equations. But, so for those of you who have studied physics, probably some dim and distant memories might be starting to kick in. And hopefully for those of you who haven't, you'll be pleasantly surprised here, because we can rewrite this system of second order differential equations, right, as, so there are going to be D second order differential equations. We can actually rewrite them as 2D first order differential equations, which are defined by Hamilton's equations. So in other words, if we solve Hamilton's equations, we solve the geodesic equation, and the solution of the geodesic equation, in other words the path, minimize the variance of any estimate under independent sampling between two distributions. So it gives you the most sort of compact path, if you will, in terms of entropy, in terms of information loss and so forth. And I think that's pretty cool. So solving Hamilton's equations defines the lowest variance, or the shortest path, between two densities on the manifold. Can anyone see any connections now from what we described yesterday with Hamiltonian Monte Carlo? So yesterday we just used Hamilton's equations to make a path. And you know, we said that, wow, we can actually make very large moves. Because this is meant to be a conservative system, we can make very large moves which are going to be accepted with high probability. And that's a property that we really need. But the other property now is that those proposals are actually going to be following the geodesics defined by the metric. And that's the problem with Hamiltonian Monte Carlo, is that the metric is not defined properly. And so if you do some tensor analysis, you'll find that the Hamiltonian with a constant mass matrix for a statistical model which doesn't have a constant metric tensor, then it will not be invariant. So if you change the parameterization of your probabilistic model, then the Hamiltonian changes, and then you know the efficiency of your method is all going to change in some way that is not entirely clear. Whereas if you define it on the Riemannian manifold as we've done, and we employ the appropriate metrics and connections, then it's completely invariant. So it's completely invariant to the parameterization, and this is exactly what we want in probabilistic modelling. So this is a very nice insight, I would say, and I think it's really, I think this is pretty cool. So solving Hamilton's equations and defining a proposal, in actual fact, defines this lowest variance path, which happens to be the most efficient or shortest path to get from one density to another on the manifold. Okay, so we've said that it would be desirable, and now I've shown why it's actually, is it too much for you? You're overcome with that insight. You've got to have a quiet moment by yourself just to reflect on these deep mysteries that are being unfolded. Poor girl. I wonder if she'll come back now. So now we have an insight as to why it would be desirable, and we don't need to shake our hands anymore or wave our hands like Neil does. We can actually point to some very crisp reasons why it's a useful thing to do. But now that we've convinced ourselves that this is a useful thing to do, what we need to achieve next is to use this in designing an effective transition operator. Now the job's fairly straightforward from here on in, really, because we pretty much did that yesterday when we defined the Hamiltonian Monte Carlo method. And so let's just go through this. We define the log density under some model. We did yesterday. We introduce our auxiliary variable. Remember we did that? But what we did is we had some arbitrary matrix M, mass matrix. Now what we're doing is we're saying that the covariance structure of our auxiliary variable is going to be equal to the metric tensor at the position theta. We then devise the negative joint log density again. Remember we had that yesterday? You know that we can interpret this physically as the total energy. And so what we've got here now is the overall potential energy has now been expanded because we've got the determinant associated with the normal distribution, and this determinant is no longer going to be just a constant, an arbitrary constant. It's going to be a function of the current position, and it turns out that this is in actual fact the measure on the manifold, but we can ignore that for the time being. Now, I guess one of the irritating things that's going to come out of this is that this is no longer what's called a separable Hamiltonian. In other words, the potential energy is just a function of position theta, and the kinetic energy is just a function of p. That's what we had yesterday, and that's why we could use this very nice Stormer-Verlet leapfrog style symplectic integrator. Now what we've got is a Hamiltonian which is no longer separable, because although the potential energy is a function solely of position, The kinetic energy is now a function of position and momentum. And that causes some interesting challenges, which we'll come to next. But the first thing we need to do is we need to convince ourselves that if we can sample from the distribution associated with this, the joint distribution associated with this Hamiltonian, that the marginal density from it will be the density that we're interested in. And some machine learning summer school algebra shows us, in fact, that that's the case. So the marginal distribution is the distribution that we are interested in, the posterior, if we're going to be Bayesian about it. So we can just steal all the ideas that we had from yesterday. We now sample our momentum from this normal distribution, but the difference from yesterday is that this normal distribution has a covariance structure which is a function of the current values of theta. And then we sample a theta from this distribution here, which again is constructed from the path that's followed by numerically integrating Hamilton's equations. In other words, here what we're doing is that this proposal is going to be obtained by integrating across the geodesics. Right? So again, we need to numerically integrate Hamilton's equations, as we saw the other time. And there's a little bit of a technical complication here, which I'll go into in just a moment. Now then, can anyone see a little fly in the ointment in the argument? So the argument was that solving a Hamiltonian which just has kinetic energy gives us a solution which is also the solution of the equations which describe the geodesics on the manifold. Now, here's what our Hamiltonian looks like.
Can you be sure that your geodesic are unique?
No, absolutely not. That was far too clever a question. It's much simpler than that. So let's just look again. Maybe an old man is going to pipe in here. Oh, Neil's got to wake up. Right? The Hamiltonian, whose solution via Hamilton's equations gives us solutions of the geodesics equations, right, described in this form here, is fine. We have a Hamiltonian that has this form and this form. So the result is based on a Hamiltonian which is purely defined by kinetic energy. So it's in the absence of any potential field. Right? So it's just free movement, if you will. Here, on the other hand, we have kinetic energy and potential energy. So it's not generally true that solving Hamiltonian's equations in this case will give us the solutions of the geodesic equations. Oh, this is hassle. Well, let's just consider a Hamiltonian which is purely kinetic. And we'll just define it as H tilde, and we say it's defined as H tilde because the metric, we'll just call it G of tilde. So we're convinced that Hamiltonians are comprised of only quadratic terms, kinetic energy terms, exactly describe the geodesic flow in the coordinate space. But our Hamiltonian looks like this. We have the log of our target distribution, and then we have the component associated with the auxiliary variable. But it turns out there is a principle which again is cutting edge mathematics that dates back to the 17th century, called the Maupertuis principle, the principle of least action. And it tells us that if we define the metric tensor G tilde by the metric tensor coming from the model which defines the potential, so in other words our probabilistic model, and we scale it by H, where H is the current total energy of the system minus the potential, right? So H is going to be constant, V is going to vary. So in other words, all we're doing is we're scaling the metric tensor of our model to obtain G tilde. Then it turns out that under this principle, that the Hamiltonian flow, so the solution of the Hamiltonian equations for H, for this Hamiltonian, and this Hamiltonian here, where G tilde is defined in this form here, are equivalent along a particular energy level, or equivalent along a particular isocontour of probability under our statistical model. So, although we don't have a global result, we have a local result that the geodesics and the Hamiltonian flows coincide on a particular energy level, so on a particular probability isocontour. So in other words, if we solve Hamilton's equations, we are in actual fact solving this second order system of differential equations defining the geodesics, where now the connection is related to the scaled metric tensor. So the Hamiltonian Monte Carlo method, defined on this Riemannian manifold, will indeed produce proposals which happen to be geodesics on the manifold, which is pretty cool. Any questions on that? Yes?
What's the small h again?
H is the current value of the total energy.
So it's not a function of theta.
It's not it's constant. Next.
Does it not result in a more peaky distribution finally?
Why?
Because you will sample from more probable you will have more probable points, so you will finally have you will sample, if you take your distribution, you will more sample from the...
Okay, that's an interesting question, but what we showed was that the marginal distribution under this sampling scheme was in actual fact pi of theta, so it was the distribution of interest. So the distribution of interest is completely invariant under this the construction of a sampling scheme like this. Any other questions? No? Just looking at me. Old man? You're happy? Okay, let me just finish off, and what I'd like to do is in the last part of the talk is try and give you lots of examples, because I think I've bludgeoned you with a whole load of concepts from differential geometry, sampling theory, stochastic processes, dynamical systems, but then you're machine learning PhD students, you know, you're really smart. Right? You've been hand-picked to come here, so you can hack it. So let me finish this part, and then what I want to do is go on, once we've finished our little break, is just spend the remaining amount of time talking about practical applications and some of the implications of that, okay? Okay, so if we, I'll run through this fairly quickly, but the dynamics now of the Hamiltonian, remember the Hamiltonian is now no longer separable, and so we can't use nice tricks like Poisson brackets and so forth to define integrators. So we have a rather much more complex form where we have these derivatives of the inverse of the metric tensor. And for some people who work with Gaussian processes, especially the older amongst us, if they look up from their laptop, they might actually see some expressions that look very familiar to them from the optimization of the marginal likelihood of a Gaussian process. Right, okay, you can now get back to your...
Preparing my slides.
You're preparing your slides. So we need a symplectic integrator for this non-separable system. And it turns out that the very nice Stormer-Verley method that we employed previously cannot be used. And it cannot be used because that is developed under the basis that the Hamiltonian is completely separable. So to cut a very long story short, very interesting story, but we define an integrator which is in actual fact semi-explicit. So in other words, if we want to update the momentum at the half step epsilon over 2, you'll see that the new momentum at t plus epsilon over 2 occurs both on this side and on this side of the equation. And likewise with the full step for theta, the new value occurs on the left and the right-hand side of the equation. So we have to solve these equations before we can update our theta and p values. But the key thing here is that this still gives us a time-reversible, volume-preserving map. And therefore, detailed balance is going to be satisfied if we employ the same acceptance probability that we used previously. So the computer scientists amongst you will probably give a big sigh of relief if you see some pseudocode. But this is in essence the algorithm here for the Riemannian manifold Hamiltonian Monte Carlo. So we just sample from our normal distribution where the covariance is now equal to the metric tensor computed at the current values of the parameters. We then draw our uniform random variate, which we'll use in the accept-reject step. And then what we'll do is we'll sample the number of steps within our integrator. So we'll set that to some random variable between 1 and some maximum value. And then what we have to do is enter this loop. We then have to solve these equations for p at n plus a half and theta at n plus 1. And then we just ripple through this n times. And then our proposed theta star and p star are just going to be equal to the points on the approximate path that we obtain from this loop here. And we then just plug those into the joint the joint distribution to get our acceptance probability, and then we accept or reject, and then we just keep looping. So you can see the only difference really between the standard random walk Metropolis Hastings and this here is, well, first of all, we have this Gibbs step, and then we have this other Gibbs step, which is really just the Metropolis step. And the proposal mechanism is just this, the solution of this system of deterministic differential equations. And that's it. Easy. So let me give you an example, which I gave you yesterday. Remember, our target density was the was this here. Okay, so by cranking lambda up, rho up to something like 0.99, then we get this very severe distribution. And we saw how the standard Hamiltonian Monte Carlo method, where the mass matrix was just an identity, did a pretty good job. Now, if we work out what the metric tensor for this model is, well, it turns out just to be the inverse of the covariance. So it's just going to be the inverse of this thing here. And therefore, the overall joint distribution, the overall negative log of the joint distribution of the Hamiltonian now turns out to be this. So the only difference here is that in the standard Hamiltonian Monte Carlo, you would just have P transpose P. And now what you've got here is P transpose sigma P, where sigma, of course, is the metric tensor. And for this particular model, you can see that the metric tensor is not position specific. It's global. But do you see a difference? If I define a path, right, of 15 steps with a specific step size, then do you see the geometric regularity now in the path that's followed, both in theta and in P? Do you remember yesterday when we looked at the path that was followed with Hamiltonian Monte Carlo? It kind of wiggled about from one end to the other, and the momentum kind of did some crazy walk. But now we can see that by employing the natural geometry, then we have a proposal which is following these geodesics. And just to allay any fears, I mean, clearly what would be sensible would be to stop here. But I've just let it run round so that you can actually see the beautiful geometric structure that comes out of this. Right? And again, we can see that the value of the negative log density at the start of the path and the end of the path, the error is not that great, indicating the probability of acceptance is going to be very high. And here's a number of examples. So, just to illustrate, we start here, we deterministically integrate, and of course this is stupid because we would want to stop up here rather than coming back to close where we were, but this is just for illustrative purposes. Right? We do the same, of course, for our momentum. Then we take this theta, this new theta and this new p, plug it into H, accept or reject, and then we sample a new p, which means that what we do is we jump to a new energy level, and we start again, accept or reject, jump to another new energy level, and on it goes. So you can see here the natural geometric structure of the bivariate Gaussian emerging in a much more natural way than it did with the standard Hamiltonian Monte Carlo. And again, that's because we are using the correct geometry for the model to define the manifold and therefore the geodesics that are actually followed. And because we're using the correct geometric structure, then we have this nice invariance property of the Hamiltonian. Now remember our Gibbs sampler. I told you we were all convinced that it was doomed. Well, here is a nice sample path for the two dimensions in our for this bivariate Gaussian. Now the first thing you can see is that both of them are highly correlated, and you can definitely see that this is very much transient. This hasn't converged at all. And what you can see here is the autocorrelation of the samples that we draw once the Gibbs sampler has converged. And you can see that, you know, up to a lag of certainly over 20, we've got a huge correlation structure. So this is really going to impact the overall Monte Carlo error. If, on the other hand, we employ the appropriate metric structure and employ the implicit geodesics for our proposal mechanism, this is what we get. Right? well, I mean, it's almost independent. There's a very small lag at time 1, but apart from that, the samples are almost independent, and the mixing is almost immediate. So the convergence to the invariant measure is almost immediate. And let me get out the statistician's Swiss roll. This is the warped bivariate Gaussian. So product of bivariate Gaussians with 2 means and so forth. But anyway, here's the distribution. And this is one that, it's a bit like the Swiss roll. One's heart sinks every time a paper appears for review with the banana distribution on it. So if we use HMC, again, you see that it's doing not a bad job. It's wobbling about. But when we employ the metric structure from this probabilistic model, you can see, how the underlying geometry is followed by the proposal mechanisms in a nice, elegant way. Okay, so maybe you want a little break now.